Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the Sky and Telescope Author Series. And I'm very happy to have Adam Block with us today. Hi, Adam.
Hello.
Where at your geolocation? Where are you at?
I am in Tucson, Arizona.
Aha, that is only about 100 miles, roughly, south of me. So I'm in Phoenix.
Yeah.
So we have the Arizona show today.
Oh, really? Oh, okay. Yeah. So I think that this show is it's good. We're both under nice skies, and it's a good day to have a conversation.
Absolutely. So you have some fascinating knickknacks behind you there. I see a thermometer off to your right. You've got that bulb thermometer over by the
Oh, yeah, the Galileo thing. I forgot about it. Yeah. Actually, the really cool thing is this guy.
Uh-huh.
I don't know if anyone from maybe the late 70s, early 80s remembers those. That's one of the little lightning storms.
Uh-huh.
But that is one of the original ones. I think that they changed the voltages eventually because people could shock themselves. So that still has its all powerful, everything in it. And I love it. And so it's one of my favorite toys.
So if nobody's ever seen one of those before, you go ahead and turn it on, and you can see the discharges between the central ball there and the glass. And so you set up sort of this electrical storm, and you can control the electrical storm by putting your hand or some other object around that glass bulb. They were very popular for a while.
Yeah, so the charge diffuses through the rarefied gas, but when you put your hand on it, you make a better connection between you and the ground. And so the charge will flow from that ball through the gas and then to you, and it makes like what looks like lightning. And it even has the wonderful sound of zzz, zzz.
It's really usually a purple.
Yeah, exactly.
Very cool.
Yeah.
Well, you have some really lovely images behind you as well. I think I particularly admire the one with the measurement there,
right
off to your right, and so I'm sure we'll be covering some of that when we get to your article.
Yeah, that's if you're talking about this one, yeah, that's actually a painting my wife made.
Beautiful. Yeah. The hand. That's really beautiful. That is lovely. Congratulations to her. That is cool. Is it one of a kind?
It is one of a kind, yes. And it was a gift to me. I'm, of course, honored to have it.
Awesome. That is cool. So, Adam, what do you like to do in astronomy?
Astronomy is more than a hobby for me. It is also a profession for me. So I have, it's astronomy everywhere, all the way down, astronomy. I work at the Department of Astronomy at Stewart Observatory at the University of Arizona, but I also obviously do astrophotography in some form. What I'm most well known for are the creation of, especially in this sphere anyway, are the creation of video tutorials that show how to, create these astrophotographs. And that is the genesis of articles like what was published in Sky and Tel.
Cool.
Yeah.
So speaking of, let's go ahead and get to it. So we're going to bring up this really lovely Sky and Tel article on picturing galaxies, tips to get the most out of your galaxy image. And Adam, take us away.
All right. So one of the things that I would like to mention before we get too far into this is that my background, just so people appreciate the perspective that I'm bringing to an article like this, is that I've worked in public outreach. So I helped develop the public outreach programs at the National Observatory from 1996 until 2005 or so.
Cool.
And then I later founded the Mount Lemmon Sky Center for the University of Arizona, where I work now, back in 2007. And both of these destinations have public outreach programs where you can, not in the pandemic, unfortunately, but normally, where you can go to the telescope and experience really wonderful programming. But as part of both of those programs, as part of both of these destinations, basically, I created these astrophotography programs or outreach endeavors that allow the telescopes to be used to generate astrophotography, either for people coming on site to be treated like a visiting astronomer, or perhaps to log in remotely or just download data that is acquired from the systems. And in the course of doing that, I've had the opportunity to work with lots and lots of data. And so that affords me practice, if you will, in processing images. And through that, I have, through time, developed a perspective in processing that I think is cognizant of, it has an awareness of both what I want to communicate as someone who is processing the images, and also what viewers are likely to see when they look at the images. And that combination of being aware of that is, I think, powerful. And so that is what I think this article taps into. Now, it's specific to galaxies, but it taps into some of those ideas. And it's a more holistic, I think, way of looking at astrophotography in general as an art form, in addition to kind of this technical thing where you have to manipulate the data and put it all together and process it with software.
And
So
that art form means that, and hopefully we'll get into this as we go through the article, or you'll add to the article, is that there are choices to be made.
Exactly.
And so if we talk about some of those choices, that would be great.
Yeah, and those choices, that's exactly what I want to talk about.
Cool.
So one of the things about the subject matter in terms of galaxies is that galaxies, I mean, an image like this looks dramatic, right, of the Whirlpool galaxy.
Absolutely.
But galaxies in general are really subtle creatures. Unlike a bright emission nebula or a planetary nebula, a bright star cluster, galaxies tend to be subtle for a number of reasons. One is that the colors initially in the raw data are not very striking, because you're looking at the average of lots of stars and everything. Everything is all averaged together, since we don't have the resolution to see very many individual structures. And even if we do, they're very, very small.
Right.
So galaxies basically are great averages of both structural information, of the spatial information, as well as the color information. It's just, everything is just kind of averaged together because they're so far away. And that requires, I think, a different approach than you would approach processing something like a nebula or something else that's really, really bright. And so you have to have that kind of mindset. When you look at an image like this, you want to choose how can you maybe counteract that or bring out more of what structure or what color something like this presents. With the Whirlpool galaxy, the elements here that we're looking at, there are so many that we have dust lanes, we have the H2 regions, which are red, we have all of the blueness in the spiral galaxy itself, and then we have the structure, the spiralness of the galaxy. Depending upon how you choose to display it, it can look very flat, or they can stand out from the disk. And those are choices that are made through different processing algorithms or techniques that are employed when you're actually working with the data. So the fact that you see the galaxy like you see it on the screen, most of those are choices that I made. It's not that I, by recipe, just went step 1, step 2, step 3, this is what it resulted in. Instead, I purposefully made sure that this was what I was looking to get.
So let me ask you a question then. So when you create an image like this,
right,
you are exploring options, choices.
Right.
Roughly how long would it take you to finalize what you think is a good scientific and artistic image such as this one? Does this take you 10 minutes? Does this take you 20 days?
Oh, well,
Where does this lie?
yeah.
Or do you revisit it after, do something and let it sit for a while and come back and revisit it?
I think that's part of the process, though I tend to, once I've reached something that I like, then I tend to stick with it. So
Okay.
I'm not someone that likes to process and then go do it again. That
Okay.
drives me crazy.
Okay.
I think the answer is it depends on the data, to answer your question. A lot of the time, though, is really spent with a combination of manipulating the data in the normal way that you do when processing and software, like I use PixInsight and other programs.
Mhm.
But then there's the decision-making part that you alluded to, and that generally requires some experimentation.
Yes.
You can optimize that experimentation and not just be randomly picking, moving sliders around and randomly picking things until you, oh, that's the one I want.
Right.
Because I am familiar with many of the processing algorithms and the effect or the look or the manipulation that they make with the data. So I know the direction I want to go, and that limits the number of experiments that I need to make. But I do need to make experiments to actually try things and then adjust things to see how it appears.
I think you hit a really a critical point there is when you're going in is you have some vision of what it is you want to show. That vision may mold as you make your choices and as you go through the data.
Right.
But there is a high level vision of what it is I'm trying to show here.
There is, and in fact, I don't mind, if you don't mind, not going in order here. And if you
Perfectly fine. Non-linear is great.
yeah, nonlinear. If you scroll down a little bit more, you'll find that I have an image of a group of galaxies. Continue to go down.
Group of galaxies.
Yep.
There we go.
Still more. Keep going. It's a long article. There it is.
There it is.
There we go. So this is a group of galaxies that are interacting fairly strongly.
Mhm.
And there are many features to this group. Now they're small features. Nothing here really jumps out or stands out in a way that would make people just do loop-de-loops. But in the very beginning, when I first look at the data, it's not even in color yet, but I'll start to see color later, right? All of these features I've already identified. I know that at the end of the day, I want to be sure that this X feature of that galaxy shows up prominently. If I'm not careful and I brighten things too much, that X-like feature will turn into a fairly clipped, featureless kind of brightness there.
Mhm.
And that would be counter to the vision that I have in my mind. I envision that, and this is the thing that really got me excited about this particular object, is you'll see that this small galaxy is somehow being disrupted in a way that there are clouds of dust obscuring matter in the foreground. That is rare. I have not seen that many interacting galaxies where you can directly see that kind of stuff. And that is easy to clobber, to not make visible at the end of all of the processing that you want to do. So I, again, was looking at that. Then where there are some very dim, the bottom galaxy has a very dim outer shell or loop of some sort that I want to make sure shows up. And of course, there are some colors I can see that, there's some redness there. Notice, again, going back to the top galaxy, to the right side of the X, because of that dust, notice how the arm on the right is yellow or reddened compared to the left arm, which is more whitish. Yeah. Again, that's a feature in the color space that would be very easy not to miss, to not hang on to in the course of processing. So all of the decisions I make for all of these features, I'm sure to try to take advantage of. And I don't know, I think I referred to it in the article. I take this from the idea of what like Ansel Adams would do. Ansel Adams said that he would pre-visualize. So he had his camera up looking at the scene, and he already knew what he was going to be doing later with his dodging and burning to get that image to what he imagined in his mind's eye, his pre-visualization of it. In a very similar way, I think that is a good way to go. Oftentimes people will ask me in workshops, in the course of processing, when you've done all of the normal calibration stuff, the question comes up, well, Adam, how do you know what to do next? This is the answer. The answer is to already have in your mind what that image looks like at the end of the day. Now you can't, unfortunately, if the object is not, if the object is blue and you want it to be red, there are constraints based on the data. So you have to work within those constraints. But within that realm, you still have a lot of many decisions to be made, a lot of choices to consider.
So let me ask then a question on this particular image. Do you apply your vision and your choices uniformly throughout the image, or
Oh,
do you
now
felt
that is
doing
an interesting question.
something here, which you do something a little different here?
And that's okay. So first, let's do the terminology.
Okay.
I would call there's global
Mhm.
processing, which means that every algorithmic process that you apply to the data is applied across the entire image.
Okay.
And then there is what you would call selective processing.
Okay.
And selective means that it could be based on, as you're describing, a particular part of the image. Now, oftentimes people will, well, it depends on what there are people who would manipulate every single pixel in an image. So there's one end of the spectrum. And then there are other people who say, you know, as a documentary thing, you wouldn't want to do that. You would only want to apply global processes that are somehow reversible. I am somewhere in the middle, in the sense that
Okay.
there are certainly selective kinds of processing that you'll do. I tend to do those for artifacts, where there are areas of an image where obviously due to instrumentation, due to some environmental conditions, whatever it is, there's some part of the image that needs to be adjusted. I don't mind selectively doing so if there is some clever way of going about doing it. Now, there is a version of selective processing that is global, but it only interacts in different, it is only applied in parts of the image because it might be based on thresholds. And here is where the line becomes blurry.
All right.
If, for example, we only want to adjust the image where it is above a certain brightness, it will only be taking effect, though everywhere, only in those places that meet that criteria. And if you only have one object in the field, for example, if you only have one thing in there, you're basically only operating on it if it's bright enough, and or you're not, you're protecting everything else, whatever it is. So this is kind of the idea of using masks that are based on thresholds. Now, it could be brightness. It could also be color.
Yes.
We could operate on the image, and if I wanted the blues to stand out more, for example, I could go to the blue channel and make some kind of contrast adjustment that will enable those blues to stand out. That's global, but it is selective because I'm only operating on one channel.
Right.
So there's kind of a hybrid of how you consider these manipulations. But in general, I'm not painting on the image, as you were kind of indicating with the mouse.
Okay.
Yeah.
So in particular on this image, was it selective or global?
It was global, with exception to what is called, there are ways of compressing the dynamic range, like an HDR effect.
Okay.
So I was using PixInsight and I'm using HDR-MT. That is what allowed me to maintain the X, because I operated on the nuclei of these galaxies because they're so bright, to make sure that that information inside was visible, though not overdoing it. And so I think now is a good segue to scroll back up to where we were in the, yeah, you can go.
Yeah, we were somewhere.
Yeah, okay, well, actually, come right back to the Whirlpool Galaxy just for a moment.
Okay.
I'll go right back up. We'll just start very quickly going back down. With the Whirlpool Galaxy, I did apply this particular algorithm of HDR-MT, and that's what allows you to see that structure or detail that goes all the way to the cores. The cores look like stellar little, blobs. And that in and of itself, as far as galaxies are concerned, is kind of a typical thing to shoot for. We're not able to resolve the core of a galaxy in the sense that the very brightest part should basically be the size of the star, of a typical star that's in your image. It'll have though it's fuzzy, something like that same point spread function. And so that's why my nuclei here looked fairly similar to stars, right? And so I'm applying that HDR-MT process to reach that point, and that allows me to show the structure that goes all the way into the center. So if you scroll down now, we can talk about decisions and maybe how important it is. So we'll stop here on this one. while you can apply these nonlinear adjustments to images, at some point there becomes a problem when the data is very bright, that if you make it all the same brightness or even worse, it's still too bright in the, say, the center of the galaxy in this case. I'm thinking more, this is everything that I'm saying also applies to nebula and other things, but here in this galaxy, in the very center is where it's brightest. You'll notice that it looks kind of grayish.
Yeah.
Right? It's lost the color. Well, it's not that there wasn't color there. If you looked at the original data, before I had blended everything together, I put this together using the typical technique of LRGB imaging. If that luminance information is simply too bright, or the color information, if it's white clipped for some reason, when I blend everything together, I will lose that color. And so that's a very important thing to pay attention to before you move along and you put everything together. So there are actual numbers, if you will, that, and this is just based on the math of how color is reproduced on monitors and so on, but you don't want to get basically above about 80% of the brightness level of the luminance. So if you have 100% brightness, you'll never be able to apply color in there. If you have 90% up to the maximum brightness in your luminance, you still just can't get the color in there. The maximum amount that you can really get color to colorize is right around 80%. And that's the ceiling. So you want to keep your values in your luminance, at least initially, below 80% brightness in order to get the color in there, or you end up with this. And I mention this because this one for me is a big one. If you look at the average, now I'm going to say not a galaxy, but an average image of the Orion Nebula, pay attention. Go to Google, look in Google and just type Orion Nebula or M42.
Right.
And notice what happens in the center of the Orion Nebula of most images. It has this issue, if you will. And it may seem like a small issue, but it's the kind of thing that can be attended to if you choose early on to monitor that aspect of the data. So that is a conscious decision that needs to be made. And if you just do it procedurally by going step by step and processing, you may run into this particular kind of issue.
Right.
Okay.
Very
so
cool.
That is an example of something that is selective in the sense that I may have applied this nonlinear adjustment to be sure that those brightness levels in the luminance were not exceeding that 0.8 about value, so the 80% brightness. And what's interesting, if you scroll, we'll zoom out here and scroll down maybe a little bit more. M31 is that, once you have access and you're now talking about these particular tools, it comes with some, great power and great responsibility, right? You can do an awful lot of things with these particular tools. So one of the funny things is that in trying to make this article, I actually found it difficult to reproduce because I'm so used to doing it, to avoid all of these issues that I feel, I want to avoid. It was difficult for me to reproduce the issue that demonstrates what to avoid. So this is a really good example here with the Andromeda Galaxy. On the left, what I'm displaying is an image that, because the galaxy has been flattened, if you will, its brightness profile is equal from the core all the way out to the outside, to the outer edges. And we'll see this in another example as well. And what that tends to do is it makes it difficult to show contrast in color and other kinds of detail. One of the arguments that I make in the article is that there are truths. Now you can choose to display them or not. And I obviously manipulate these elements of an image, but there are truths to the data. There are truths to, I say truth, I say there are observed features of galaxies. Galaxies are brighter, literally, in their centers than they are in their outer arms. So if I apply a process which changes that, that's a choice. And it could be detrimental depending upon what you want to communicate. And so for me, I enjoy showing that particular aspect or feature of galaxies. Galaxies are brighter in their center. And even if that means that it's more difficult for me to display those central dust lanes, that's okay for me, because I am balancing the ability to be able to see contrast in the center with this other truth about galaxies. So the one on the left, a lot of people like. I tried to make it in a way that a lot of people would like it. They have very high contrast. You can see every tiny little tiny detail of dust lanes going all the way to the core.
Yeah.
Where the one on the right is more subtle. But to me, it communicates something that I feel kind of viscerally has that galactic feeling to me. It's not just a structural object. It has other components to it that I want to have included in the presentation of the object.
Nice, very nice.
So if we scroll down some more, let's see, we had the, this is another example of this, where it's not so much these two versions of this image, of this galaxy. It isn't so much that there's that flattening of the image, right? Instead, there's another element that I like to consider, like in a galaxy like this. Those dust lanes, they have a feature to them, which is that they have a color to them, and they also show what I would call the attenuation of light that comes through them.
Yes.
So in other words, as light comes through dust lanes, and this again applies to galactic nebula in all sorts of situations, but as light comes through dust, the attenuation, the amount that the light is attenuated is lessened, is a feature.
Yep.
And if you raise the contrast, you will basically remove that feature of it, which is you make those dark, well, you make the dust lanes even darker, and it makes them in some sense opaque. And so the opaqueness to me, though it makes it easier to see the structure, it removes this other element of the galaxy itself.
Right.
So that's what I'm demonstrating here. And, people obviously have their own choices, but this is my perspective. And the reason that I'm coming with this perspective is I would say you want to consider what you might be losing by making an adjustment. Just because you have this one element that is suddenly revealed or much easier to see, you may have other elements that suffer because of it. And I'd like to add one more thing, which is it's another subject entirely, which is there are particular, I'm going to say, preferences that people have when they look at almost any image. And Ansel Adams is a great example. Ansel Adams would dodge and burn images to increase contrast for the most part, where he wanted that contrast to be increased. Contrast in and of itself, there is an evolutionary preference for us to want more and more contrast in an image in general. So if you were to show people images of particular scenes and whatnot, generally speaking, the one that has more contrast is the one that is going to be preferred. And that extra clarity, that extra bit of information that you get between seeing the bright and the dim things and so on is just cross-culturally preferred. But just because it's preferred doesn't mean that you always have to employ it. And I think that that's something that in this article, I'm trying to communicate. In other words, if you make a cake has sugar in it, right? You make some treat, but this doesn't mean that if you add, 5 cups of sugar instead of 2, that somehow it's going to make that cake better.
No.
Evolutionarily, we prefer sugar, but it doesn't mean that we always need to have, the most sugar possible in our cakes. I don't know. That's a terrible example, but
no, it's a great example. I like to cook, and I know exactly what you're talking about.
Okay, so making that mixture, that ensemble of whatever features or colors or so on, is what I'm trying to do here. And it's a way to look at astrophotography and image processing in particular. This isn't about the tools now. This is really about assuming that you have that proficiency with the tools. What are you going to do with them, right? So that's what I'm trying to do here. That's what I'm trying to show. Okay.
And I'll just add on just because I can, because I actually ran into this the other day. So I was making lemon poppy seed muffins. And if you're really trying to bring out the lemon flavor of the muffins, it helps to decrease the amount of sugar in order to bring out the lemon. Because otherwise you over sweeten and you taste the sweetness, but you decrease your lemon. And so there's a little bit of an analogy here of choices like that.
Good.
Although our brains may prefer more sugar, more sugar.
Yeah, yes, that's right. And so again, on this meta level, really what I'm talking about is that, we as artists, as astrophotographers, there are things that we potentially want to communicate. Now, some people say that what I'm talking about is just make an image and don't worry about it. But I think that there's a way to internalize what you want to present and what other people are going to see. So being able to appreciate both sides of the equation, I think, is a powerful thing to do. Because if you want to make a captivating image, something that catches people's eye, or communicate something, I generally make images for public outreach, and it may be instructional in some way. Appreciating what both sides of that equation see, or could potentially see, can really help shape the way in which you render the image or present that information. I truly believe that. And, some people think that some of the images I've made are good. So I'm going to stick with it.
I think some of them are pretty awesome.
Yeah. So, okay, so we'll scroll down. Yeah. Now, the other topic that I cover in here, which is important, deals with other elements of image rendering that are obviously important, especially with galaxies. Say, for example, a noise reduction is important for galaxies because they're so faint and the signal to noise is very low. One of the things that happens, though, is that, depending upon the kind of mask that you might employ. So this is another one of these examples where we're going to apply a certain degree of noise reduction based on a threshold of brightness. Okay. So we don't want to apply noise reduction where the signal is very bright. The stars are fine. You don't need the centers of stars don't need to be blurred anymore, or the details of the galaxy that are bright don't need to be smoothed or blurred. Mm-hmm. But the rest of the stuff can be blurred, and it should only be blurred depending upon how bright it is. So if it's semi-bright, it only gets a little noise reduction. If it's, the sky background, then you give it the full amount. But depending upon how you apply these techniques, especially with masks and so on, you'll see in this image, I don't know if it comes across very well, but if you look at the star has what looks like a great, it has like a little punctuated graininess surrounding it in the halo. The halo of the star, you'd want to be relatively smooth, right? And so if you have this harsh transition between, say, the edges of stars and so on, that can take away a little bit from the image. Now, you have to be someone who likes to maybe zoom in. Not everyone, you'll find, publishes their images at a resolution which even allows that kind of discrimination. Yes. But for me, I am processing images so that they look reasonable to me at 200%. So that's the level that I work at. If things look reasonable to 200%, then I know at all scales of the image that I ever presented at, it's going to be fine. Mm-hmm. And so here then at 200%, you can kind of see it. And what this means is that I needed to make probably the mask, especially in the bright things around stars, a little bit larger, but perhaps also apply some kind of blur to that mask so that the boundary there, the edges, have a nice transition between sky values and bright things like star values.
Mm-hmm. That may not be all that unrealistic either, right? You can sort of look at it as sort of a clumpy mass loss.
Yeah, that's okay. But the problem is that I've zoomed into one star. The thing is that there are 1,000 stars in this image that look like that, and that becomes the problem, right? Okay. And I don't. And so then below here we have, there are considerations that you might want to make in terms of composition. One of the funny things is, this isn't really composition, but it's another element, which is that if you have an image where there are very many bright stars, sometimes when people process images, say of galaxies, they, in my opinion, are overly concerned with the appearance of the stars. In other words, they're processing the image to make the stars look great at the expense of the galaxy.
Okay.
And to me, that's backwards. To me,
Mm-hmm.
I would prefer, if I'm going to do the balance of whatever decisions that I make when I am processing a galaxy, I'm going to make sure that the things that I'm applying to the galaxy really are more important. They're given the priority. And if the stars suffer a little bit, well, then I'm going to do what I can to balance that or mitigate those issues. But the work that I'm doing with the galaxy, those decisions, I consider that primary. Where it becomes interesting is where a star, say, like in this example, is really a very important part of the galaxy, if you will, because it's right there in the, in your face.
Right.
And so then it becomes more important to make sure that that star looks good at the end of the day. So then the decisions that you make really do take into account both the galaxy and the star. But I would encourage people, when they're looking again at their data and they're making the decisions about processing that information, to consider the object that you're working with to be, the primary thing. And then you try to moderate or balance whatever the other artifacts are of these other elements of the image.
Mm-hmm.
Then now on the very well-known idea of composition,
Yep.
This image doesn't have it, but if you have maybe more than one galaxy, but you have a bunch of small galaxies and a big one, maybe you put it off to the side, the major galaxy, so that it kind of has a balance in the frame.
Mm-hmm.
So I will often rotate images in such a way that I think that it communicates better, a better sense of, what you're seeing in the view. There's also kind of just the way your eye looks around the field that for some images it's jarring unless you put it in a particular orientation. Some images, it doesn't matter. I turn the image around and it's just like it's amorphous. It doesn't really do anything no matter what you do. Another thing that I prefer to do, though there is no real, it's not critical, but I just prefer it, is that we do tend to take an earthly view, even though we're looking at things in space. So there's this idea, I'm not saying this looks like a landscape, but there is an idea that things that are in the foreground would be below things that are in the background. Things that are in the foreground that are, say, dark or have higher contrast because they're closer to us,
Right.
I would tend to put below those features that are further from us. So the choice to display the galaxy like this, putting the, I don't know how to do this on the camera, but putting one edge, it's not exactly edge on, right? The
Right.
foreground edge being below the background edge, if you will.
Right.
And
Right.
that is signaled to us by the dust lanes. That's how I know that it's that way.
Right.
Is something that I generally do with galaxies. On the Whirlpool galaxies, face on, it doesn't matter. But that's a choice that I often make.
Right. Oh, good. Great. Very cool. All right.
This particular image, I think in this example, it served a multi-purpose. It was one of these examples where, again, the noise reduction becomes important because you have this inner structure that you want to maintain. And it's not shown here, but if you look at the high resolution version of this image, there are delicate little dust lanes right in the very center. They look like little wispy hairs that you want to protect. But then going out from the galaxy into these tidal tails, of course, you want the noise reduction. There's very little in the way of structure there on small scales. So it's okay that that gets more smooth. But the other thing that this image really demonstrates is this idea of the nonlinear compression of the brightness levels, where again, I've used HDRMT here. Sometimes people look at images and they have this, sometimes they have this reaction that they need to either have two forms of the image, or maybe they take a short exposure and a long exposure and try to put them together. I have found that there are certain tools that do a very good job. It used to be DDP, but nowadays I happen to use in PixInsight this tool called HDRMT. It does a fantastic job of being able to, when you apply the right parameters, to allow us to see, what's going on inside by knocking down on that brightness, but doing it in a way that I think has a natural look to it. Because if I showed you the image, hopefully on the right, because the center image, that's like the raw data. I mean, that's what you would get if you had no modification to those brightness levels. That's what you would see.
Okay.
So working then towards the one on the right requires that nonlinear adjustment.
Yep, it's beautiful.
Yeah.
Does a very nice job. So I imagine you're setting some sort of, not just points, but you're setting a curve between those points on the nonlinearity.
No, HDRMT works in a very different way.
Okay.
It works in the wavelet domain, which means that you're actually messing around with things that are at a particular spatial frequency, a particular scale is what you're interacting on. And it has some other parameters which control the strength of this HDR adjustment. So it has an ability to compress these brightness levels, but also at a particular scale. And that gives you almost an infinite variation in terms of the kind of application that you would apply. I will mention now, if anyone is using PixInsight, that there are some dangers. It is possible to introduce artifacts, number one. And number two, that parameter space is very large. And that often makes this particular tool something that people often, when they first try to use it, they say, that looks terrible. I'm not going to use that. One of the interesting ideas in image processing is that there generally are no defaults. So, sometimes in again, procedural or recipe of steps, people might think that, okay, I'll do this and do this and do this. And if it doesn't work, it's just because, maybe the algorithm wasn't right or something.
Right.
But oftentimes those algorithms that have a very large parameter space, that have that large number of possibilities, they are more difficult because you don't know where in that parameter space you need to be to give you the result that you want. But once, with maybe some practice or some deeper understanding of how the tool works, you can find that level more quickly. And then you'll find that that tool is indispensable, really.
Nice.
I would hope, maybe this isn't the perfect example, but I would hope that when people look at some of the images that I've produced, they wouldn't necessarily know what processes I did to reach the result. That's what I would call a natural look. It's the look that I can't tell what you did, really. It looks natural, right? Yes. If I see that high contrast and flat, kind of profile of a galaxy or something, I know what happened. I know what you did. If I see the central region as it had that loss of color, again, I know what's going on in the processing steps. But if at the end of the day, I look at an image and I can't say what happened, it looks great, based on the decisions that astrophotographer made, I would call that a high quality result. And that's what I strive to do on my own personal image processing.
Cool. So let me ask, what advice would you give for maybe people who are just starting out in astrophotography and would like to do some of this? What are some of the next steps they could take? And if they're already somewhat advanced along the line, what would be some of the next things you could do?
Well, I think, again, part of this is the takeaway from the article. I think that if you're a beginner, what I would say is that obviously becoming familiar with the steps that are necessary for doing the image processing, that is fundamental, and you just have to do that. But have an appreciation or an understanding that in the future, you're going to reach a level of proficiency that will allow you to make decisions and go beyond that kind of recipe of putting the image together.
Mhm.
And how you want to present the data, the decisions that you make, that's what makes this, gives it kind of that unique fingerprint in terms of a result. So just know that that's there. There is no necessarily right or wrong, but there are, and this harkens back to this other idea, there are truths to astronomical objects. So there are constraints. And you'll find that although you, as a beginner especially, you may go beyond some of those constraints, that when people look at an image, they'll say, well, that looks awfully funny. Usually the reason it looks funny is because one of those constraints has been, well, gone beyond, I'll say.
Right.
Yeah, okay. So that as a beginner. Now, as a more advanced image processor, I would just say the philosophy of taking inventory of what is in an image, and this is especially true of galaxies, initially taking inventory and having a purpose, having a direction that you want to travel with purpose, not just because the data took you there in some way and it was like the ebb and flow, you are the flotsam and jetsam of image processing. That's not it. You want to be in control of this of the ship. I don't know, I'm doing all these analogies on the ocean of image processing. This is terrible. But having that purpose, I think, is what I hope people take away from the article. When I originally submitted this article to Sean Walker, he asked, can you write an article about processing tips for galaxies? And I wrote this. His response to me was, well, that's different, because I think that this is, I hope, a different way of approaching astrophotography. Once you have that proficiency with the tools,
Right.
you go to this next level of what to do. Yeah.
Yep.
I basically, I want to be like the Bob Ross of astrophotography. That's what I'm shooting for here.
Awesome. Or Ansel.
Bob Ross. I'm not going to. Ansel he's above me.
Okay.
Bob Ross was someone who could illustrate. He could communicate
Yes.
what to do and why he was doing it, and he was happy doing it, right? There were happy trees. Well, I tried to present some happy galaxies here.
Awesome.
Yeah.
Cool. All righty, Adam, thank you so much for sharing your article and extra material, bonus material beyond the article on imaging galaxies and other things.
Great. I'm glad to have had the session with you. Thank you.
Cool. All right, everyone. Thanks. We'll see you on the next one.